recorded. So if we invite you to come onto mic, you can decline. We've got videos turned off, so hopefully everyone's okay with that. The chat will be recorded as well. So yeah, please just be aware. Right, well, thank you. Thank you all for coming along. It's great to have a good turnout here. This is, I think, the fourth foray into home energy systems for us. So hopefully that means people are liking what we're doing. We have two presenters here today. Let's just check this is going to work. There we go. Yes. So I am Richard Lane, and you just heard Polly's voice down the line a moment ago. And we are both part of the energy systems team in Carbon Co-op, which is a not-for-profit community energy cooperative, assisting our members and the wider community in reducing household carbon emissions and energy use. We have quite a good reputation for whole house retrofit, so a lot of pioneering work with that and low carbon technologies and energy system innovation. We offer training courses, sell specialist services, run large scale innovation projects, and carry out consultancy work for other groups and businesses. We have, well, we have, actually, my notes for this say we have more than 200 members, because that's what we had when the first time we gave this. Actually, we've got about 250 now. So we also do advocacy and campaigning and policy work as well. It's a great organisation, and we hope you'll be, if you don't already, we hope you'll follow us in future and take part in our events. So about this webinar, we have, we're dividing it in half. So I'm going to be running the first half, and Polly will be presenting the second half. There'll be a Q&A session after each half, so one in the middle and one at the end of the webinar. We have a Q&A system, which you can use to submit questions at any point. And during the Q&As, you can also use the raise hand button on your Zoom app to ask if you want to ask a question. We encourage you to use the Q&A system, write it down. When it occurs to you, we might not pick them up if we think they've already been answered, but we'll try and make it reasonably interactive. We'll also try to respond to comments as they come into the chat box. So it's always good to know that people are out there and engaging. So don't hold back if you want to do that. I'll be monitoring the chat whilst Polly is presenting and vice versa. And then we'll have a very brief feedback form at the end of the webinar. So this is the content today. We're going to talk about the context for home energy systems, the heating systems, low carbon heating systems, solar photovoltaics, domestic batteries, smart meters, smart tariffs, electric vehicles, integration and automation. And to kick us off, a little bit of a poll, just so we know who's out there and paying attention. What are you thinking about for your own house? Let's have a listen. Let's see, what do you got? Oh, failed to launch polling, error 4401.
I've launched it, Rich.
Oh, right, okay, nice one.
Is that okay with you? I got involved.
Okay,
so
that's cool.
People are viewing questions. Should we give them a couple of moments?
So yeah, we'd just be interested to know what you're thinking about for your own houses. Can people see those? Anyone?
There
we go. There we go.
It's happening. How exciting!
A tense moment always, isn't it?
It's a very tense moment.
Okay. Yes. Okay. There's so big popularity for EVs and heat pumps. Oh, so that's surprising show for solar thermal. That's good. The classic. Home automation and controls. Okay, with 42%, that seems to be. Last chance. There's if anyone's having trouble submitting, there are two questions. You may have to scroll down to see the second one. Ah, all right. Apparently you have to answer something in question 2. Yes, thanks, Jonathan. Okay, that's so. Yeah, you might have to put something in the other box to submit the poll. Ah, listen, Zoom, a joy. Oh yeah, that seems to have fixed it for a lot of people. Great. Okay. Well, let's. I'll stop now. So that actually, no, Polly, you're in charge of the polls, aren't you? Can you?
Yes, do you want me to end the polling now?
Yeah. Let's
I will.
share the results of that.
So I can share the results, but
Yeah.
still keep
Let's
it
do it.
open just for some last minute people.
Okay.
So what low carbon technology or other change you're considering? We've got EV and charger at 38%, 8 out of 21. Installing an immersion heater or heat battery is coming in at only 10%, 2 people out of 21. PV system, 8 again, so that's very popular along with the EV charger, 38%. Underfloor heating, similar to immersion or heat batteries, 10%. Heat pump, any variety, 52%. Solar thermal, 43%. Switching to a dynamic tariff, only 10%. Home automation controls, yeah, is 29%, so a third. And then more than a third of you are considering a battery at 33%. No plans yet or can't in current house is a 10% response. And also if other, obviously that's not quite. Oh, sorry, someone can't get into the poll. Okay, we'll call yours out. And then other heating systems came through at 33%, other energy storage 33%, or an alternative system not mentioned 33%. They're all
Yes.
even.
That reflects the So not 30. Yeah. People are just ticked because it seems you have to enter one.
I have to.
Two. So
A
you have to.
glitch in the matrix. Sorry, guys.
There you go. You live and learn. Right. Okay. That's interesting. So yes, good to see the popularity of heat pumps, and that's not so surprising. Solar thermal, a little bit of a surprise, high performing there, but and the EV is not a surprise. Yeah. Okay. Let's press on then. Anyway, let's see. We'll come back to that at the end of it, and what we'll be interested in is if anyone's changed their minds or had a rethink during the course of the webinar. But anyway, got a lot to go. Let's kick off. So first up, we're going to talk about the context. Why do we care about home energy systems? Well, it's probably quite obvious to say that our houses are a major consumer of electricity and of energy in the UK. About 30% of all UK energy of all types, that's second only to transport. And 3/4 of that consumption is in the form of gas, which is used to heat our living spaces and water. And that's a fossil fuel. If we're going to get to net zero and tackle the climate crisis, that is something we've got to address. So any plan has to tackle our houses. And the plan, well, until relatively recently, the plan was for net zero by was for an 80% reduction on 1990 levels by 2050. In 2019, I think July 2019, we adopted the net zero target for 2050. And that kind of jumped most of the projections that people had been working on before that. I think it's fair to say that we still don't really have a clear idea of a strategy for government to get to net zero. But one thing we absolutely can be sure is that we need to reduce the amount of energy we consume, and we need to electrify it. We need to convert more of our energy consumption to be electricity instead of being fossil fuels. So I say we haven't got a policy. What we do have is lots and lots and lots of strategies, scenarios, and analyses. These little infographics come from the National Grid's future energy scenarios. These are updated every year, and this encapsulates what I've been saying, really. So almost all homes in 2050 will be retrofitted with insulation. Energy use for space heating will halve, and that they reckon about a third of that will come from insulation, and the rest of the reduction is in converting to heat pumps, which are more efficient than electrical heating. We'll hear in a moment. 25 to 40% of homes will have thermal storage in the form of a hot water tank or a heat battery. And they reckon between 20 to 30 million EVs on the road in 2050. There's about 39 million at the moment. They have different scenarios that have different combinations of opportunities and technologies. But electrification brings its own challenges. As we switch our use to electricity, we have to generate more. So these graphs are of generation capacity on the grid approximately today. No, there are 39 million vehicles on the road now, not 39 electric vehicles. Did I say electric vehicles? I do apologize. There are 39 million vehicles on the road now, not electric. I beg your pardon. Thanks, Jonathan, for correcting me if I misspoke there. So this is generation capacity on the grid now, and 2030 and 2050. Now, this is the least ambitious scenario from the National Grid's future energy scenarios that still meets the net zero target. So what this basically shows us is the kind of mix we'll have on our grids. And what I want to underline with this is that there are a few implications that come from this. So first of all, economic considerations are significant. That electricity is more expensive than gas, about 3 times the cost for a unit. So if we're going to be switching to electricity, energy is probably going to become, on average, more expensive. The peak load on the grid will be massively increased. So the amount of energy we're pushing through the wires will go up, and we'll need to reinforce or somehow manage that. And a key thing also is that we'll be dealing with a lot more intermittent sources. So the little red bars I've put next to those graphs indicate the amount of generation that is non-dispatchable, which means you can't decide when you want to have it or not. You know, we know that solar and wind are intermittent because our climate change denies delight in telling us this. But that intermittency will have consequences. Will mean that you get dynamic tariffs and things like this. We'll talk about more what you can do to deal with this later on in the webinar. But it will also have implications for people who are in fuel poverty, because if the price of energy is going to vary and you can't choose when you have a certain need and you don't have the choice, then your energy bill will probably go up. So there are lots of considerations economically and socially while we're talking about electrification. Anyway, so that's the context. We are now going to have a little look at the systems that are going to be in our smart home of the future. And the first thing to say about our home of the future is that this is not what a home of the future will look like. This is a thing called the Integer House. It was a smart home built in the late 90s, which gives a model of what they thought future homes would look like. I think they thought the future was further away than we know it is now. We know that the future homes will look more like this. They're going to be the homes that we live in now. 80% of the homes that are going to be standing in 2050 are already built. And we add about 0.6% of housing stock every year to total. It's the fabric of our homes that's going to be changing, and what goes on inside them that's going to be changing. So we'll plunge on in. The first system we're going to look at, the big one, as I said before, the biggest single use of energy is in heating. So we're going to look at low carbon heating. First thing to say about this, tackle demand first. The only clean energy is the energy you don't use. Heat exchange, if you do we call it a fabric first approach. You improve the insulation, your airtightness, you design to reduce the need for space heating. And that is an excellent long-term strategy. Heat technologies change, but if you use, the less you use, the fewer problems you have. So that said, you are going to need some heating. We're in a country where, especially in the north, I don't know where you are, but in Yorkshire, you definitely need some amount of heating. So there's options and different systems here: space heating and water heating, dry systems, wet systems. Dry systems, easy to install. Wet systems, pumping water around your house, or they may require expensive changes to household plumbing. All of these have their place. There's a role for all of these in future energy systems, and we're going to sort of sweep through them quite quickly now. So first up, direct electric heating. It's the most basic thing. You basically put electricity through a load, heat up a resistance, and that's it. But you can make it more complicated. We're all familiar with oil-filled radiators and hot water immersions. You can also have wall heat mats, panel radiators, and infrared radiators. These are cheap and they're easy to install compared to central heating. You've got electricity in most rooms. It is expensive as a fuel source. Gas costs 3 pence a unit. Electricity costs perhaps 12, 14, 16 pence a unit, depending on where you are in the country. There are things you can do about this. You can use time of use tariffs. If you can store it, or if you have low demand, you can often synchronize when you want to use it. If you have a well-insulated house, then you can choose when you want to use that heat. And you can store it in an insulated hot water tank or a heat battery. But storing energy as hot water is the cheapest form of energy storage there is. If you know you're going to use it, it's massively more cost efficient to store it just by heating up water. It's a simple technology. It's an order of magnitude less expensive per unit than pumped hydro storage, and another order of magnitude less than even the best battery that we have. So that's the simplest one. A little bit more complicated, storage heaters. It's a similar idea to that. So you store it in bricks or some other ceramics or some storage medium like this. You can use cheap off-peak electricity. They have a bad rep. They're already installed in many properties. They're cheap, low maintenance. Again, you have this problem with expensive, the cost of electricity. As I said, they have a bad rep though, because older types had bad heat retention, not much controls, and ultimately they don't do much if you've got a badly insulated house. So if you've got a good high performing house, thermally performing house, then the storage heater becomes a very good technology to install. And a lot of modern high spec passive houses will just be heated entirely by direct electric heating, with no heat pumps or anything like this. Next, district and community heating. This is a big topic, so don't want to talk about it too long. You have a network of insulated pipes built through a city or another settlement. You send hot water around a circuit, pipe it into people's homes. Either goes directly through radiators in the old school, and nowadays it's more, you have heat exchangers per property, and the heat source will be central, and that can be anything: fossil fuel, nuclear, biomass, problematic, biomass at scale, solar thermal or geothermal. The network losses are significant, anywhere between a few percent and up to over 60%. Even in new build, I've seen some small district heating systems where you're getting 60% heat loss. So a study I saw in Sweden gave a typical figure of 12%. So it's a lot. It's a lot less efficient than having a boiler in each house, But if the heat is free, if you've got geothermal, solar thermal, or if it's a byproduct, then it's a very tempting option. So there are a lot of them in the UK. I was surprised to learn over 17,000 heat networks in the UK. They provide about 2% of UK demand. They're expensive to build, and they're not necessarily cheap. So even though you've got this scale, it actually can be that once you've paid to be connected to a network, you find that your heating bills have gone up. So they can be upgraded. Yes, you can upgrade the heat source, but a practicality of this is that typically you design your plant and your network, you design them for a particular demand, an existing or anticipated demand. And then so it kind of locks the whole thing together. If you want to retrofit your houses to reduce the energy demand, suddenly your boiler can't perform optimally. And vice versa. If you want to change your boiler, then you may have, if you want to change it to a different technology, then you may have to look into making sure the house is on that side. So retrofitting insulation might have a knock-on effect there. It's a complicated subject, as I say, a lot to talk about, but not time now. So next up, however, the one that you've all told us you're interested in, well, not all of you, but the stars of the show is the heat pumps. Thermodynamics, not magic. They work like a fridge or an air conditioning in reverse. And I'm going to try and give you a very brief how does a heat pump work, because it's a complicated process. Here goes. So we put an evaporator in an environment that has low-grade heat at low temperature, and we can concentrate that. That's our source. We want to concentrate it. We pump a fluid through that evaporator at low pressure. Now it's at low pressure, it wants to boil. It wants to expand and fill the space, it wants to become a gas. So in order to do that, it sucks in energy, sucks in heat energy from the surroundings. Then we compress that working fluid, squish it down. Now a squished gas, suddenly it's got no space, it wants to be a liquid again. So it does that in a condenser. As it changes state, it sheds energy, because liquids is sort of a lower energy state than gas. So that's the condenser, it's turning from a gas to a liquid. It sheds its home inside, it sheds its energy inside our home or inside a water tank. Just as it's nearly comfortable again at a nice pressure and temperature, we then push it through an expansion valve. That drops the pressure, and now it wants to turn into a gas again. This poor working fluid just can't get comfortable. We're messing it around. That process was invented in 1834 by a chap called Jacob Perkins. And the brilliant thing is that I've said evaporator and condenser, actually they can work in either direction. So you can switch it, and some models do this. You can switch so that it's a heat pump in winter and an air conditioner in summer. And you can move heat from, as I say, air outside, or from a water source, or you can do into the air or into water. So you can have air to air, air to water, water to water, water to air. There's all kinds of, it's basically just taking heat from one environment and concentrating it. So it doesn't convert energy, it just pushes it around. It takes a bit of energy to do that. So the performance of a boiler, we call it its efficiency. It's the percentage of chemical energy that it can convert into useful heat energy. For a heat pump, what we actually want to know is how much energy out can we get for every unit of energy in. So it's not the same as efficiency, although it's kind of analogous to it, and people will quote COB, the COPS, is a very key performance metric of a heat pump. It's the heat output divided by the electrical input. So typically, so for a COP of 3, you get 3 units of heat energy out for every 1 unit of electrical energy you put in. Seems like magic. It's thermodynamics. Typical COP for an air source heat pump between 3 and 4.5. It depends on the kind of the temperature outside, the amount of lift you're trying to give it, the amount of concentration you're doing, and it varies with the conditions, as I say, with the temperature. So the key metric is a seasonal performance factor, which is an average COP over the year, and it depends heavily on your local climate. Here's so yes, as I say, you've got different options of heat sources. Ground is better than air, actually, because you want a nice stable temperature, big thermal mass. If you've got the space and you've got a lawn or a ground or a croquet lawn or a tennis courts or something, if you're that kind of homeowner, then you can install a ground sourced heat pump underneath that. That's great. With air, you've got a problem that obviously the air temperature varies massively more than the ground. You can get frosting on it as well. So, you know, when it's very cold, you start having ice form on it, and that will hit your efficiency. So that's and that's the kind of thing that the performance depends upon. You will probably need new radiators. Heat pumps work well at producing steadily a low sort of temperature, what we'd consider something low, like 29, 30 degrees Celsius, whereas boilers tend to operate at 70 or 80 degrees Celsius. So in order to get the heat out of them, you need different kinds of radiators. So the one on the left is not massively bigger than conventional radiators, but it is bigger and it's a bit more expensive. It also works really well with underfloor heating as well. That on the right is showing the pipe work for an underfloor heating system before the screed's been put on it. They do take up a bit of space. There can be issues with the conservation area. They're not massive. The one on the left there is showing a condenser side going into an immersion tank, which is not necessarily required. You can get equivalents of combi boilers. You can get heat pumps that directly heat the water and coming into your house. They're not as efficient inevitably because you're trying to get a bigger temperature lift out of it. So that's going to be more energy intensive. So it's a really good pairing to have it with a hot water tank. The center shows us the sort of scale, the size of a unit outside there. And the one on the right is actually a bidirectional air-to-air unit. So that actually just has a duct to the outside, and that works either way. That's either an air conditioner or a heater just sucking in the outside, or sucking in the heat from the outside air and expelling the heat and heating up the warm inside. So it's not about the mass flow, it's about the energy flow. It could be a direct replacement for a radiator, no external unit, but it does cost 1,700 euros. So yeah, not a bit beyond the budget for most of us, but it's designed for historic buildings. How much do they cost? That's a key question. £6,000, £8,000 all in for installation. The maintenance costs are very low, so that's excellent. And this is from the Centre for Sustainable Energy, gives you the idea of yearly savings. That, if you do the maths, that's about a 60-year payback for replacing an A-rated boiler. That's a hell of a long time. You can save more if you've got local, you're generating your own energy. But the thing that really makes it a goer is the renewable heat incentive. So this is a government subsidy which pays for renewable heat, obviously. And you mean for biomass, which, well, sometimes it's renewable, sometimes it isn't, but it qualifies. It's for biomass, for air source, ground source, and solar thermal. You get this a payment from the government in the same way as you used to get feed-in tariffs for every kilowatt hour of heat, every unit of heat you consume. The support varies according to the technology between 6.9 pence per unit for biomass, all the way to 21.3 for solar thermal. That for a 4-bed house, that you can see the range there that it brings in. You can calculate how much you get from that on that website there. And it's closing for non-domestic properties next March. It is carrying on beyond that for domestic properties, but it is not going to go on forever. And there are some plans afoot for the next thing that's going to be replacing that. It requires you to have an NCS registered installer and an EPC on the building, and it brings the payback time from 60 years down to about 5 years. So that's a game changer. Solar thermal we mentioned there. Now, this has been around for a long time. Rooftop collectors, the sun hits them. It's just solar heat from the sun. containing there's normally a little working fluid inside the tubes, which then exchanges into a fluid going into a hot water tank with a little pump to send the whole thing around. There'll be a heat exchanger there. It's a fairly simple system, but it's a lot of plumbing. UK plumbers have got a poor track record on solar thermal, though. So I'd say approach with caution. You will need an immersion top up in winter if this is going to give you the least benefit when you need it most. So if you're going to do an immersion top up in winter, then maybe just get the heat pump instead. It's a question. They have high efficiency, but if you're going to get a heat pump, because of course you can use grid electricity or PV, well, actually, it's not bad because of the copper multiplier on the heat pump. PV efficiency of 20%, copper for 80%. It's not that much less to do PV and heat pump, and you've got a complete heating system which runs off low carbon energy from the grid as well. So something to think about there. Solar PV, we're kind of straight onto that already. This is photovoltaics, generating electricity from light. And we're talking about grid connected systems today. We do have a separate training on off-grid solar, which if you're interested, follow our training schedule and nag us to do it, but it's kind of a bit hands-on, so it's not very COVID-able. So yeah, rooftop PV is what we're talking about here. You could do it on land if you've got land, but most of us don't have enough for that kind of shenanigans. This is what a system looks like. You've got strings of panels on your roof connected in series. They're brought back, they generate DC, they're brought back to an inverter, which converts it to AC, to 240 volts, 50 hertz AC, which is what we use. And there's isolators there for safety. That brings it through a generation meter. It then reaches the fuse, what we call it informally the fuse box. It's more probably the consumer unit or distribution board. That's where it meets your local demand from your appliances in your house. And then, of course, you've got your local grid connection coming in through a consumption meter. What I've drawn here is just having two strings, so two pairs of panels connected in series. That's not very plausible. You might have a string of panels on one roof and another string on another roof. But this is just sort of an illustration there. Just some terms while we're talking about this. I've already mentioned kilowatt hours, a unit of electricity. That's what you tend to get billed for. A watt, is a unit of power, the rate of consumption or transmission of energy. Kilowatt is 1,000 watts. A kilowatt hour is 1,000 watts consumed for 1 hour. With solar panels, a key metric is the WP, the watts peak or kilowatts peak, which is the rated power of the panel. It means that basically you turn on a sort of a standardized level of light onto one, and it will generate its rating in watts peak. So 300, typical rooftop panel is 300 watt peak. Shine a light on it, which is a standard light, which is a sort of a representative amount of light you might get on a decent day. That will generate 300 watts. But the nameplate power rating of an array may be less than the total PV rating. Efficiency, just for a illustration, 1 kilowatt hour, 1 unit of electricity is what you get contained in about 100 milliliters of petrol. So just shows how energy dense petrol is. Efficiency is the proportion of the solar radiation that hits it which can be successfully converted into electricity. There are hard physical limits on that. You won't take all the energy out of every photon hitting a panel. You won't even capture every photon. The current record is 46%, but 20% is good for modern rooftop PV panels. I hope that helps. So if you're going to get solar PV on your roof, you're going to design a system or someone's going to design it for you. These are the things you'll take into consideration: the size, the orientation, the shading, which basically, the options you really have are the bits of roof or wall you have available to you. You've got to think about what kind of inverter you want and who you're going to get to install it. So let's rattle through these. When you're thinking about how big an array you want, generally you'll want to fill the whole roof, but maybe not. It depends on your motivations. So there's different ways you can approach this. Some people want to be self-sufficient as a principle. Some people want to save money. Some people want to help with decarbonisation of the grid. So you've got to think about your demand, how much energy you'll be consuming. And of course, it's actually, unless you're fitting a battery, it's the amount of demand you've got when you're going to be generating. So where if you've got solar panels facing south, you're going to get, well, some midday is when you have the most sun. How much energy do you use at midday? For most domestic properties, not so much, although of course that's changed dramatically since we started doing this webinar series. Panel size itself is standardized. It's about 1 meter by 1.7 these days. That's almost always. If you don't get a standard panel, then they cost a lot more. So you've got to think about your budget. Panels prices, they start to increase quite a lot above about 350 watts peak. So the more efficient panels cost more money. But a key thing to realize is that the overall system cost starts going down with size, because it's not the panels that are the most expensive thing. As you get bigger, the panels become a less significant part of the whole installation. The scaffolding and so on is often the biggest cost. So if you're going to install, there's an argument for installing, going big. Rooftop PV is not a money spinner. Export income has, there's no feed-in tariffs anymore. Export income is pretty low. It will most likely decrease unless there's some dramatic unforeseen policy changes. And even the prices of solar panels aren't falling rapidly anymore. This 4 kilowatt peak system cost is 2019 price inclusive of VAT, and that's from Green Business Watch. That gives you a break even in about year 17. So you have to have the system 17 years before it breaks even. Before they closed the feed-in tariffs, that was 13 years to break even. And in the glory days when the fits were sky high, a lovely, 30, 40 pence a unit, then you'd be getting a payback in about 7 years. But if you are going to do it, then, as I say, the bigger a system is, the quicker it pays back. So go big. Here's some people who've demonstrated that ably. They've got a tiny little terraced house, and they've managed to cram 11 panels on it there. They've got more panels on their little terrace than I've got on my semi. So yeah, good on them. Just talking about roof, where you want to point these things. Now, as I say, you may not have much choice, but there are some considerations here. That there's two things: tilt, we talk about, or elevation, and azimuth, which is the direction that it's facing. So historically, you just point it south. That's the azimuth. Just point it to the south, and that generates the maximum yield. But that's not necessarily best anymore, because you want to match when you're consuming energy, and the peak for domestic consumption tends to be in the evening. So maybe you want to point it to the west. Also, the midday solar peak can cause problems for the grid. Everyone generating solar energy at a point when there's low consumption, then actually you start getting problems. And we've recently seen the emergence of dynamic tariffs, which was agile tariff, and in the middle of the day, sometimes that goes negative. So you do not want to be selling at that point. Now, at the moment we have a guaranteed export price, that may not last forever. So you don't want to be, you might want to think about pointing it west, as I say. You might think about or just having a nice spread. That's a lot of PV arrays are doing nowadays, especially the commercial ones. Here's a nice, this one's their alternating rows of west and east facing panels, very shallow. So that's to create a more even generation profile over the day. And this one is from the Netherlands, but this is happening in the UK. There's the Graveney Marsh Solar Farm in Kent, which is doing that. And similarly, over the year, you get an effect where traditionally you'd tip your solar panels at the angle of your latitude, roughly. I mean, if you put them on your roof, you haven't got many freedom of movement in this, really. So you haven't got many degrees of freedom in this. So but if you've got a flat roof and you want to tilt them, then flatter. When the sun's higher in summer, you get it flatter. It's going to generate more in summer. Tip it up higher when you're going to get more in winter. So you might think about lifting it a bit to match your energy consumption, which will be higher in winter. And we've got an example of that. This chap here, this is a nice retrofit installation. He's got his terraced house to near passive house standards, so he's not requiring much heat demand. His heat demand will be in winter. He's got a Tesla Powerwall and a heat pump. And so when he needs that energy, he wants it to be maximized in winter. So he's put them on vertically on his gable end. So there you are, that's thinking about things laterally, almost literally. Shading, again, if it's on a rooftop, it kind of is there or it isn't. But the way it works is basically each one of the cells in a solar panel is a sort of a separate current source, and they tend to be connected in series. So if you shade one cell, then that's a bit like connecting a flat battery in parallel with a good one. It'll bring the whole string down. But having said that, modern panels do have bypass diodes, so it won't knock out the whole panel, but it will affect, you will get a multiplier effect from any shading on a panel. And you will consider the shading over the day. And perhaps there's a strategic thing you can do where, okay, in the middle of the day, you need less power. So perhaps you can, if you've got a chimney or something like this, perhaps you can arrange the panels such that the shadow falls over the panels in the middle of the day when you're not going to need so much energy. There's that kind of thing. So there's quite a lot of detailed design you can do with a PV system. Inverters are a key part of the system as well. There's different types, string or multi-string optimizers or microinverters, and they have, these days it tends to be multi-string inverters, which allows for having a string of panels on one roof aspect and another on another. Other types protect against panel failure and do sort of clever optimization if you've got shading and things like this. Panels are incredibly reliable these days, so protecting against panel failure is not such an issue. But it may be that you want an optimized system or a string of microinverters if you've got a particularly nasty shading situation. Monitoring is standard in inverters these days. They tend to be Wi-Fi connected, but there are other standards. If you want to connect them to another system or not send information to the cloud, most inverter manufacturers have their own kind of online portal systems. So there's one for LuxPower on the left and SolarEdge on the right, and you can kind of log into that and see all your data. These are both battery systems here. And there are non-proprietary systems available. So Open Energy Monitor has an open source system based on a Raspberry Pi with current clamps. A bit of a word about location now. You can put your inverter, the typical place is to stick it up in your loft. It will get hot up in your loft. It'll have big variations of temperature. That doesn't do much good for the longevity of an inverter. They do last well. I mean, back in the day, you used to expect to replace your inverters after about 10 years or so. These days, they're lasting pretty well. But putting them in a loft is not going to help that. You could put them next to your meter or down away from the solar panels. The issue there is that the longer your DC connection is, you get losses at low voltage that are far more significant than you will after the inverter, if you see what I mean. The DC losses are greater than the AC. So if you put the inverter right down near your meter, you've got long wires up, you're going to be losing energy through that. Again, not masses, and the energy is free. So if you're going to, check out your installer, of course, this is obvious. The quality and the cost of installers is hugely variable. So do this, that's the standard sort of advice you have for any contractor. Check the reviews, ask to speak to the existing clients, get a guarantee on the roof work, try and find someone who's registered with the Solar Trade Association. And also, if you want to get the Smart Export Guarantee, then you'll need your installer to be Microgeneration Certification Scheme registered. Almost all of them are. Check your roof quality as well. Make sure if your roof is likely to fail before the panels do, then you may want to address that first, because if you have to take them all off and put them on again, someone told me that cost £1,000. It added £1,000 to the cost of replacing the roof to take the panels off and put them back on again. But you don't have to think about the long term. You can just stick them up and do it. As this person has. I kind of, take my hat off to this person. That's possibly just the very early stages of a full passive house retrofit to that barn. I don't know. See what they've got in mind. I'll keep my eye. That's somewhere I cycle past intermittently. Next up, then, batteries. So there are many types of electrical storage. Battery is an electrical storage. It's converting electricity into chemistry, and then you can get electricity out at a later date. It'll have some loss, but yeah, it's a very useful thing to be able to do. The only real kind of battery, the really real relevant in a domestic context is the lithium-based electrical storage. So I think the one on the top right there might be an old lead-acid array, which is problematic. You could theoretically do that. That's huge, heavy, and toxic. So lithium really is the only game in town. It's worth, as I said before, that the hot water center, if you're going to store energy, and you need heat, then store it as heat because it's so much cheaper. Yeah, store it as heat as in water cylinders or just in the fabric of the house itself. And a lot of houses are built with large thermal masses that will actually store energy. That's far cheaper and more cost effective than having a heat pump, which you will run later off a battery. This on the left here is a system installed by Carbon Co-op back in the day. It wasn't me that did this, but it illustrates the different parts. You've got your battery inverter, the pack at the bottom, and then there's some junction box communications. Systems are a bit smaller than that these days. The one on the right, of course, looks very swish. That's the Tesla Powerwall, the famous one. The junction box and communications is often integrated into the batteries now. And the one on the right is probably what they're more going to look like. That is, yeah, the famous Tesla Powerwall. Costs an arm and a leg, but it contains a lot. And it's nice that both these pictures have got bicycle wheels. I like that. If you are going to get a battery installed, there are two ways of doing this. So there's AC coupled and DC coupled. This is a bit technical, but just quickly, just AC coupled keeps the battery separate from a solar system. It's good for retrofit. It means you can add the battery on to the system as it is. It's less efficient to use. That means in order to use the power you've generated on your roof, stored in your battery and consumed it, it's got to go through an inverter 3 times. So DC coupled is more efficient. It's less flexible slightly. It allows you to have DC circuits, which I always liked as a very elegant solution. You can have a DC circuit in your house, low voltage stuff, charging your phones and your laptops and so on as a DC system. Maybe, if you can switch things to DC that don't need to be AC, that's quite elegant in my mind. Okay, big proviso on batteries. They will almost never pay back under current situation. So you need to know how and when you generate and use electricity. It's rare, given, as I say, the current situation, it's rare that your battery is going to pay back within its lifetime the cost of it. And the environmental case is also weak. They cost the resources the embodied resources they represent. It's a tricky one, but there are ways. There are 3 ways in which your battery can pay you back, and these may change. The relative strengths of these will change in future. So, first of all, self-consumption. Yeah, that's what we imagine. You're not using the energy when you generate it, so you store it in the battery, and then you use it later. But someone else will use that energy when it goes to the grid. It's not wasted. Someone else will use it. I mean, it might get stored elsewhere at the grid level in future, perhaps as well. So, it's not the end of the world. That's not wasted electricity. Second use is price arbitrage. So this is what systems are now being developed to deal with the dynamic tariffs. So you can charge up your battery from off-peak, so economy 7, or from agile tariffs. When prices go negative, you can fill yourself or gorge on cheap energy or free energy, or and then you can actually release it back to the system. So you can gain some income from that. That's difficult to achieve at the moment. Again, we'll see what happens in the future. That may change. That will be a game changer to the economics of domestic batteries. The grid flexibility. Now, it's a bit abstract, this one, but this has value to grid operators. As I said, when we have a lot of intermittent generation and a lot of, obviously, you've got an intermittent demand, then there is a big job to do matching them. So one thing that will have value and people will be paid for, and organizations are already paid for, is providing this flexibility. So people will in the future be paid by grid operators to operate their batteries. So please charge your batteries now. We need more demand. There's too much generation, not enough demand. We need to generate more demand. Please, everyone charge your batteries, charge your EVs. And later on, they'll say, we need that much energy back, please. And so you'll have a certain proportion of your storage will go to help manage the grid. So the problem is that those 3 uses are in contention. You can't do all of 3 things at the same time. You've got to have some kind of balance or some kind of apportionment between them. So that will require smart controls to balance and optimize. So, and this is where it's all at the moment. This is what a lot of work is going into. Is it worth it? Okay, I've kind of preempted this a little bit. The simplest way is to try and estimate how much of your annual electricity bill will be reduced for a given battery size. It may last 10 to 15 years before needing to be repaired, replaced. Multiply the saving by 15 and compare the total cost. So it's a big spreadsheet kind of exercise there if you want to do it. And then if you want to look into it, then you've got to start looking into your crystal ball a bit to make an estimation of what the kind of value of dynamic tariffs and flexibility income will be in the future. And this is something we're looking at in Carbon Co-op. So if you're interested in this kind of stuff, if this is your boat, then stay in touch. Sorry, your bag, not your boat. If it floats your boat or if it's your bag, again, then get in touch and stay in touch. Yeah. So yeah, a couple of things. It's early days with domestic batteries. There's a lot of gotchas, a lot of uncertainties. Battery manufacturers talk about capacity, rated capacity, usable capacity, nominal capacity. There's a lot of terminologies used a bit loosely, especially in the kind of marketing bump. Capacity can mean its actual ability to hold energy, or it can mean its ability to discharge, in other words, the power. So these days, and also, are they talking about the absolute maximum that it can physically contain, or are they talking about the absolute maximum that you can discharge from it without damaging it? So this has got a bit better recently, with manufacturers giving a fixed capacity with guarantees, and they sort of over provision the batteries. They kind of the battery will physically contain more energy than it will be advertised, if you see what I mean. So the charge and the discharge rate can be very different as well. You need to look into a lot of things when you're designing a system. If you discharge very fast, you'll again shorten the life of the battery, and it will contain less. So yeah, there's a lot of variabilities. Space may be at a premium, and they do generate noise as well. If you've got them in your loft, then the inverters, the batteries won't bother you too much, but they aren't totally silent. Your battery needs to be installed with a solar PV system to get a 5% VAT, otherwise it's 20%. You may have to notify your DNO if your capacity is over a particular threshold, though most systems have a grid limiter built in. And then, you've got to keep an eye on it. You can't just trust that it's going to be working and doing what you want. It's a complex system. There's a lot that can go wrong. Okay, that brings us to the end of the first part. So I've already seen one question in the chat, and a very good question, and one that I'm embarrassed not to have answered. I said DNO, didn't I, without thinking. DNO stands for network operator. Damn it, I've forgotten the D. That's embarrassing.
It's okay.
Distribution network operator. Oh, blimey, sorry.
It happens to the best of us.
Yeah, distribution network operator, because there's also the ESO, the electricity systems operator as well, which is the national grid. The DNOs, they're your what used to be your electricity board. So the DNO for this area is Northern Power Grid, where I'm sitting in York, and it's Electricity Northwest for Manchester. And it's also, to confuse things further, the DNO is becoming the DSO, which is the distribution systems operator, which represents a changing role. Okay, do we have any questions in the Q&A?
We sure do. Let's get them up.
Okay.
So air-to-air heat pumps are not favoured. It's not so much a question as a declarative. They're not favoured by German subsidies in the UK or Germany. Air-to-water or ground source does qualify for subsidies. Thank you, Alex. Why is air-to-air frowned upon, from Alex? So that's the query.
I wouldn't say they're necessarily frowned upon. They're certainly, I would say a to-water system is better, because you want to be heating a thermal mass. Air is not a good thermal mass. If you want to heat water, then you send it around your radiators and your floor. You get a better kind of energy retention. You get more flexibility. If you want air to air, then generally you want it quickly, and yeah, you need it when you need the heat. You just get less buffering. So it's not frowned upon, I'd say, but in most situations, if you can use air to water or water to water or ground to water, that's going to be a better solution for most houses. Okay, what else have we got here? Would a ground pump dictate what you can do with the outside space? Does it have to be grass paved, or would a densely planted garden still work? That is a good question. It will, to some extent, affect it. Again, I'm not an expert in this. This is not something I have much experience of, but generally they do tend to be fairly, how to put it, inert, sort of or static kind of environment. So, grass, tennis courts, car parks, that kind of thing. I think you'd be asking for trouble if you wanted to plant it up with, with trees that were going to mature, because you don't want to be pulling up a whole copse of fruit trees to repair your underground heat pump coils if they go wrong. Right, a heat pump at 30. So, right, okay, I said that a heat pump putting out a steady 30 degrees is good for space heating. A heat pump at 30 degrees can heat up your hot water to 50 degrees. No, that's not the case. Heat pumps can produce theoretically any output temperature, but yeah, you want 50 degrees is a good sort of maximum to consider for them. But yeah, you'd want a nice, if you've got underfloor heating, then 30 degrees is a great temperature to be outputting. If you don't need hot water, then your heat pump can operate at 30 degrees and get maximum efficiency. If you want to heat your hot water up, then it can jump up to 50, do that job, then go back down to where it's more efficient again. So keeping that temperature lower is going to give you better efficiency. Are there solutions now for PV to water heating? Sorry, are there solutions now for PV to water heating storage to space heating? I don't fully understand that question. Jonathan, would you like to come on mic and explain what you mean there? Oh, hang on.
Yeah.
Hi.
Can you hear me? I'm muted.
Yes,
control.
Got you.
Can you hear me? Can you hear me?
Yeah, we can hear you, yes.
Okay. So I've got a method of generating electricity now. This is called PV.
Great.
Can I use it to heat my space now in an efficient way and storing it along the way? I mean, I'm generating electricity at noon. Can I store it and heat my space in the evening?
Well, the efficiency of that is limited by the efficiency of your space. So the ability of your space to retain heat. I mean, if you've got a normal house or a leaky house, then the answer is no, really, you can't do that efficiently. If you've got an immersion tank, then absolutely you can fit a diverter. You can heat up your water when the electricity is being generated. So anything. And before it exports to the grid, it will dump that energy straight into your immersion tank. And that's a brilliant thing to do. And actually, we can link into David's question here as well. Heat batteries, such as SunAmp, if you haven't got space for a hot water tank, then you can install a heat battery, it's basically just the same job as an immersion tank, but it uses phase change materials. And as such, it can actually do the same job in a fraction of the volume. So they reckon about a third of the volume of an immersion tank for the amount of energy stored there. So those are two options for PV to do water heating. I hope that's answered the question, Jonathan.
I think so, yes. It was... yes, I think you answered it with the second part. The second part of your answer, yeah.
Yeah, I mean, if you think of anything more, then pop it in the chat and we'll come back to it later anyway. Okay, thanks. We don't have much time. We've got to sort of plunge on. We've got a lot of content in this. How deep does a ground heat pump have to go? Not that deep, to be honest. I mean, just a couple of feet is enough. It depends on how much width you've got, actually. I mean, if you've got a very small area, you've got to go down deep. If you've got a very wide area, then you've got to go across. What sort of area is needed for an average house? That's a good one. I don't know the answer to that. I suspect probably not as much as you imagine. I think I certainly know that there are projects in London where they're heating a whole tower block from the green space around it after retrofitting insulation. So yeah, again, the area needed depends on the performance of the house. But yeah, I can't give you a very good answer on that, I'm afraid. Well, that's kind of a very similar answer to Simon's question. Vertical heat pump straight down. Yeah, it's possible. It's very disruptive. Again, you're going to need some fairly hefty machinery to do that. I mean, ground sourced heat pumps are expensive, there's no doubt about it. And most people are fitting air source heat pumps because it's just a hell of a lot easier. I think I'm going to have to leave it there because I've got to hand over to Polly for the second half. Oh, yes, we've got some. Alistair, Alistair just made a comment in the chat. I wonder if you can make that to all, you've just sent it to panelists, Alistair. Perhaps you could send that to everyone if you could resend that same comment. Anyway, Polly, are you ready to take over?
I sure am. Yeah. Do you want me to do that? I'll just quickly add the comment to everyone.
Oh no, I'll do that. You share your screen and
okay.
There you go.
Okay, I'm going to override your screen sharing. Let's make sure. Hold on, give me 1 second. There we go. And hopefully people can see this.
Got it? Yeah. All right, I'll mute.
Amazing. Okay, so smart meters and smart tariff. So you may have heard some things about smart meters. They might not be very nice. They've had a bit of a bad rep. The rollout's been a bit of a negative one in the press. And the smart metering program it's an ongoing national project. So don't believe your energy supplier when they say you haven't actually paid for this service. So it's aiming to install a not meagre percentage. We want 50 million smart gas and electricity meters to be installed by the end of the rollout. So that's in about approximately 30 million properties. So those are domestic, but also smaller and non-domestic sites throughout the UK. And it's important to know that because we're paying for this rollout through our energy bills, if you're having that discussion with your supplier, you might want to frame it in that context, because this is a charitable act. It's actually an obligation. Your energy supplier, it doesn't matter who they are. And actually, smart meters aren't a new thing. So we're a little bit behind the curve in the UK, much on this, that there have been existing very large deployments of smart meters already.
Polly, your audio is breaking up a bit there. I don't know if there's anything you can do about that, but your audio is sort of seems to be cutting out. I don't know if there's any way you can boost yourself
at all.
You?
Oh, how about now? Is that any better?
That's better, yeah.
I'm hunching over. From a health and safety perspective, not great, but I do yoga, so we'll be fine. Is that any good? Okay, I'll keep going.
It's better.
Great. Okay. So, I mean, that said, while we might not be ahead of the curve, smart meters are actually based on established standards, and we are doing quite a bit better now. We've got about 30%, I think, of them installed of our aim. So, yeah, why do we need smart meters? So you might have noticed there are systems at the moment like the Zigbee SEP, which are already known to some people and maybe even in your current home setup. And they've been adapted for use in the UK to actually support the monitoring of our energy use, but they've got lots and lots of other functions, which is why we're very interested in them. So colloquially, they are known as SMETs, which actually stands for Smart Metering Equipment Technical Standards. And the first and generation examples are the ones you might be familiar with. So the rollout is actually for SMETs 2. And these are basically a system that has this minimum standard system so that they can actually be utilised by householders, and that you then have the insight into half-hourly incrementals of your energy usage, which is great because it creates a lot more user autonomy. You can become more of a prosumer, so rather than a passive consumer, you can actually work out what energy you might be producing as well as utilising, which is fantastic, and it changes the dynamic of how we use our energy in our homes. So it's quite an important milestone in that regard as well. Obviously, with the pandemic, we've had some road bumps that we've hit. So there's been around, this is probably a little bit out of date now. I'm not really sure what the latest stats are. I don't know if you are, Rich, but we've got about 12+ million of the SMETS 1 were installed. They're migrating over to SMETS 2. A lot of them are going offline or becoming dumb in that process, unfortunately. There's more than 4 million SMETS 2 installed now. So we're approximately 30% of our target's technically been met, if we're being nice to ourselves. But the extension to 2024, we're going to call that an extension or horizon rather than a solid deadline, because obviously we've had many, many hiccups with this rollout. One question that you might want to consider is the 100% target even realistic? Is it desirable actually? Do we really need to hit that? In a sense, it's more about the support and the uptake of the customer sort of belief in the smart meters, that people are actually interfacing with them, using them, understanding them, and finding them functional in their homes. And also, essentially, something that's an attribute and not just another gadget that they may or may not find a use for. So the reasons that you may or may not know that smart meters might be hugely beneficial, from Carbon Corp's perspective, it's something that Carbon Corp's been waiting for a long time for the SMETS2 rollout. It gives us this incredible insight into the entire population's home energy usage, and that can signal a shift, a huge shift, not to understate it, in how we deliver energy efficiency measures. Because we have this granulated data, which is householder specific, and we can measure and bill every half an hour of our energy usage in a systemic way. And this can also mean that we can pass on any savings through that efficiency to people who are the end users of energy. But it doesn't actually necessarily mean energy savings in the carbon sense, unfortunately. It could just mean financially. But it can also help us reduce the amount of infrastructure changes we need to make to the grid by using energy in a more efficient way. Also, it ensures that we can connect with distributed energy resources a lot better. So things like solar that you're generating in your household, for example, we can ensure that we tap into those by a much more granulated approach on a local grid level. And we know that in order to really harness and utilize renewables to the absolute maximum effect, we really do need smart meters to do that. And that said, I've actually got smart lighting in my house, and I was going to use my mobile phone to turn the lights off because it's getting dark now, and I can't actually do that right now. Perfect example of how to not interact very well with your smart gadgets in your house. Let me just scroll through. So in terms of the structure, give me 1 second, I am actually going to put my light on. 2 seconds, guys. It's a living example of someone trying to be energy savvy but affecting their own eyesight detrimentally. Yeah, in terms of how the rollout's going and what we're doing with our smart meters where we need them. So obviously they have a really large install base, and historically SMETS1 involved the supplier. So the architecture with SMETS1 is very similar to other smart metering systems. So it's using a mobile network for its communications. The supplier contract is with different suppliers, and there's a back-end service, so all of the digital and data produced comes through to the supplier. And most of those SMETS1 meters will be enrolled and adopted into the DCC. So that's the Data Communications Centre. And that central communications system is also in place for SMETS2. I'll just quickly hurry up because I'm aware of time. So SMETS2 has a different architecture here. As you can see, there's just 2 communication networks. It's a lot more elegant and simple in its architecture. There's one single back-end service. The access is provided via DCC users, and also it will include suppliers that, what you might notice here is they're not essential to the architecture. So it's been designed to remove those gatekeepers. So suppliers' roles have changed, and that enables an opening or an opportunity for the creation of new energy services, something that Carbon Corp's really excited about. And we actually offer a smart meter data service where we can gain access to smart meter data now in the same way that suppliers do, to enable more insights for ourselves, to support you as an energy service company, a nascent one, and also for yourselves to find out what you're doing with your energy and how it works in a more granulated way on a half-hourly level. So it's incredibly important in that regard as well. And also, if you are interested in this energy usage visualization service, we can share a link at the end of the session. But sadly, due to many factors, the global pandemic being a big one, we know that the rollout has been slowed. So for a lot of you, you might be sort of stuck with a dumb meter. But just to have a really quick look about how smart meters fit in. So you've got your appliance, you've got a gas meter, you might have an electricity meter, your smart appliance, and then the in-home display and a communications hub. And sometimes that can take the form of other, like an energy assistant as well. And then you can sort of see the flow here, but I'm going to skip through quickly because of time. So as I said, the rollout's sadly lost a bit of momentum. It's quite difficult for some people to access the data because things aren't changing quickly enough. There's not necessarily that much support on the ground, which is unfortunate. And you know, we do actually need that data. It's quite important delivery of some grid services, for example, higher resolution energy data. For example, if you want to prove or verify you delivered demand reduction or energy generation that you said you have. And it's also potentially really helpful to unlock, automatically analyze and work out if the readouts are faulty or if something's not working in a system at home. So they are incredibly important for that as well. But unfortunately, they're not currently capable of 15-minute settlements. So it's not that granulated yet, the data. One of the main reasons that smart meters have to have widespread settlements of domestic and SME usage is at 30 minutes is because prices at the moment in terms of electricity market prices, they are available every 30 minutes. So it kind of synchronizes with that. And then having these different 30-minute pricing mean that you can actually, as we spoke about before, build in a much higher efficiency level and also lower systems cost because you're operating in this granulated and responsive way, and the use and the demand are kind of more in balance. But unlike economy 7 or 10, the price of electricity varying every half an hour can be a little bit more difficult from a consumer perspective to interact with. So here's an example of a tariff from Bulb. You can see the classic peak time where people are discouraged to use energy. Obviously, it's going to be a lot more expensive at the time of day when the use is the highest and the strain on the grid is the most extreme. So the expense of energy is much, much higher and much more carbon intensive as well. And then the classic one is Octopus Energy, which at the moment I think is still kind of leading the way really in terms of offering a dynamic smart tariff. So with this Agile, one of their many, many tariffs, you can access these half-hourly energy prices. And so obviously with your power usage being tied to that wholesale price and it updating daily, so you don't have to keep up with it, but you are paying in this kind of agile changing fashion. So you're paying for energy almost in real time according to the actual cost to consume it at that time. So obviously there are pluses and minuses to this. It sounds a bit kind of like a bit of a gamble, but it's not necessarily. Just zip through. So obviously in summary, at 4 p.m, as we've already touched upon, rates go up, but also with the Octopus Agile tariff, those rates will be updated for 24 hours. You can actually see ahead of time the predictions and the rates that you'll be expected to pay. And because they're calculated through smart meter data, it again centralizes the need for and the use of smart meters. And also if you have, as we mentioned earlier in that diagram that we skipped through really quickly, a consumer access device that can enable you to connect your smart meter locally in your house, and that can also provide you with much higher resolution data, which again really helps you take advantage of this new breed of tariff really, and also to engage with grid services, like offering sort of working with flexibility, using your EV to do that and that kind of thing, but we'll talk about that in a bit. And then obviously responding to plunge pricing alerts when prices are dropping. So obviously sometimes prices will go into the negative and things like that, and you can shift your electricity loads, like within the EV charger being a high load, or your immersion, for example, representing a higher load, or batteries, if you have that kind of system configured. So then you can really take advantage of saving or using power at the times of least and most use and align with that and help flatten the curve. So here's an example of what that looks like in a graph. So from the Octopus Agile tariff perspective, so obviously this is representing a sea change in the way electricity is used by homeowners. It's not for everyone, but obviously if you're offering people this different pricing system, then you want to show them how they're going to be able to take advantage of the tariffs, and you have to be able to weather the peaks and the troughs of the electricity price. So this graph shows peaks and troughs with a very pronounced peak in the late afternoon, which coincides of course with peak usage. And then at other times, the price does seem to be lower than uniform pricing, as indicated by the dashed line. So you can see that. And that obviously in that sense, you can see it sort of begins to pay for itself, because you start to take advantage of the rate, which is actually much better than the competing rate shown in the blue. And a smart export guarantee, again, this is another example of sort of different ways in which we can dynamically price and use our electricity. So the smart meter is again core to this working. A smart meter enabled export tariff is for generators. And I think Rich mentioned it briefly as well. So it is kind of a replacement for the feed-in tariff, at least in policy terms, and it is an export-only tariff. It's now a requirement that all large suppliers offer smart export guarantee tariffs, where you'll be paid for any power you export to the grid. So in this sense, it's actually technically a subsidy, as it's possible for export prices on the market to go into the negative, but suppliers still have an obligation to pay you above 0 pence per kilowatt hour, even if this is the case that we've gone into a negative. You can opt for the smart export guarantee for your export component, but you can also keep your feed-in tariff if you already were on that for your generation component to sort of maximise income. And as things currently stand, there are few suppliers, there are actually a few but not many, who are offering a higher smart export guarantee rather than fit generation. But you really need a smart meter to take advantage of that as well, to take advantage of that service. And as you can see, the tariff ranges are, they're not massive. So normal tariffs are obviously confusing, but the pitfalls, again, as we've already touched upon, are that it's quite difficult for consumers to understand or determine if a tariff really fits their usage, and you may not be able to even find that out unless you've already monitored your energy usage in a very granular way, or you've had that kind of insight through the use of a SMETS2, for example, or a home energy system and a home assistant, so that you can see what's going on in your usage and generation as well if you generate energy in the home. So they may not be appropriate for everybody, and if you can't necessarily flex your demand or shift larger loads, then it's not really going to make a big difference to you. For example, if you just switch a few lights off, what you really need is, if you've got an EV or a battery pack, a battery will, what have you, will be able to shift that load, because it really would represent a material saving, and you notice the difference to take advantage of price shifts. So yeah, it's very kind of specific to the household and to your capacity to have that insight, to take full advantage of those kind of opportunities and challenges represented by smart tariffs. In terms of the electric vehicle, we'll just quickly whiz through this. So we do have to decarbonise our transport. It's absolutely incumbent upon us, and we're wanting to do that. Obviously, we've phased out as a policy now in the UK, diesel and hybrids as well, and petrol cars by 2035. But in order to phase them out, we need to have the infrastructure to take on a much higher capacity of EVs. And obviously in the UK, battery operated vehicles, they will have lower carbon emissions, but they are not zero carbon, as a caveat. So it's great if you have an electric car, but there will obviously still be a little bit of emissions attached to running that. It's very difficult to be completely zero carbon when you're operating a car, no matter what kind of car it is. So on their own, we know that operating these battery electric vehicles isn't enough decarbonise the transport system. So we do need a large modal shift. As the caveat, we need other kinds of transport as well to take over from personal car usage. We need to think about carpooling, we need to think about bikes and other modes of transport. But there is, in a sense, the fact that EVs are essentially batteries on wheels, and they represent really big loads that we can shift and support the grid with. For example, there are batteries now as large as 100 kilowatt hours coming to market. If you compare that to a Tesla Powerwall being a 15 kilowatt hour battery pack, they represent a huge load to help support the electricity system. They're far larger than anything you'd normally install in your house, and their mileage range is improving all the time. It's now between 100 miles depending on what model you get. And most charging is happening at home or at work, I think now. About 80% of charging is happening in those places. So we need our home systems to be set up to manage that. And obviously there are lots of elements linked to this as well. So again, a remainder of that charging has to happen as well en route. So at rapid charge points, for example, garages, motorway stops, that kind of thing. You might have seen these points, you maybe can use them. And you might want to understand the cost of charging your EV if you're thinking about getting one. So this is a sort of worked example. There are obviously, variations dependent on the vehicle and its capacity and its rating, but all you need to know really is the performance energy efficiency of the vehicle, and the calculation here is shown at 4.5 pence per mile at the moment. So it's still much, much cheaper than running a petrol vehicle, although obviously the upfront costs are very, very different from a standard petrol vehicle. So if you're charging a car with grid electricity, as I mentioned, it also means you're creating grid emissions. So it's not a zero carbon way of moving yourself around, but currently these are still down to quite a low figure. So 0.2 kilograms of carbon per kilowatt hour. So once that's the average intensity But obviously, once you actually factor that in to charging the car, it comes down a bit more to 0.1% in terms of usage. So while there is a large amount of embodied energy and carbon in the battery in terms of the life of the battery and the way it's produced, there is still, you know, a significant saving of carbon in terms of running the car itself. There are some other emissions associated with running an EV, obviously particulate emissions. So while you don't have the tailpipe emissions in terms of gas pollution, you do have some particulate matter that comes off things like the wheels. Dust is created as well as the car's used. These are the sort of things you might imagine would happen. It's quite difficult to offset all of these things for obvious reasons, because, you know, it's a locomotive, and there are going to be always a downside to the upside. But as you can already see, back in 2015, in terms of like the efficiency, you know, there's a phenomenal difference between running an EV and, you know, a standard car. And in terms of the emission capacity, you can see the tailpipe emissions in blue on the left. I mean, they're huge. Even in the most, you know, efficient car, they're still significant. Whereas comparative to the electric car, and this was back in 2015, so things will have come on a bit since then, you know, that there is no tailpipe emission, obviously, and the fuel cycle is pretty low. The only sort of standout one where it's not great in comparison to the average car is in Germany, but in all of the other ones, the EV pips all the other vehicles. So it's, you know, it's pretty impressive. There are lots of levels of EV charging. You might be aware of these. We're going to whiz through them. You've got slow, just 3 kilowatt hours with a 3-pin plug. Fast, between 7 kilowatt hours and 22 kilowatt hours if you're set up for that and might be a commercial vehicle. They're more likely to go up to that level. It depends on your system at home. And then the rapid charger, which is a more significant level, between 43 kilowatt hours and 150 kilowatt hours. It's quite significant.
That's
on average,
kilowatts, not kilowatt hours, just to
oh, sorry, kilowatts. Yeah, sorry guys. Schoolboy error there. So yes, it's basically, you can see the kind of stratification there. So it's quite a huge contrast from a slow to a rapid charge. And in terms of connector types, we don't have time. It's not interesting enough. We're just going to whiz through that. You will get the slides if you wish as well. We won't force them on you. You can certainly have a copy if you'd like to. So obviously charging at home, there are lots of factors that will affect that, and it's important to know that it's not just the theoretical rating of your charger that affects charging, it's the whole chain of how your charging might be limited or bottlenecked here. So it could be everything from your grid connection, or, you know, the weakest link, if you like, could be anywhere in this chain. So the charging of your EV might be limited by the slowest part within the chain. So the grid connection will be of a particular size. In the UK, it'll be your standard sort of single-phase connection, so it's probably like 100 amperes. And on a site generation or house electrics, you might have limitations there within how they are structured. And your charger obviously has its theoretical rate, which will be its absolute maximum rate that it can't exceed. But EVs also have limits on how much charge they can accept, so kind of how quickly they can charge. So even if it can theoretically charge up to 21 kilowatts, the grid connection might be limiting it. So your car, you know, in actual practice might be capable of 7 kilowatts. So that's the kind of summary of expectations from, you know, what it says on the tin versus what it might actually do in practice, and some of the reasons why that could happen. There are a lot of advantages to electric vehicles. One of the main ones, in a sort of more altruistic sense, is that they can really support the grid. So you might have heard of the term vehicle to grid. So by enabling us to export power back to the house and grid it's connected to, some EVs are actually, you know, capable of creating this two-way relationship where they're pushing the power back to the grid when they're not in use. The average car, I think, is out of use 96% of the time. So, you know, that represents a big amount, a huge chunk of time spent doing something very useful and, in a sense, quite altruistic, but also really financially lucrative. Well, I say really, potentially. But more than anything, it's supporting sort of the grid infrastructure and supporting electricity when you're not using the car. So those vehicle to grid chargers are currently a little bit expensive, and they're not necessarily standardized. So sadly, this might mean that we can't really adopt them more widely until that happens, which could be five years or so from now. But, you know, it's something that's in the mix, and it could dramatically change the economics of home energy. by supporting the grid. And then these costs can be passed on to the consumer, these cost benefits. You might have heard of smarty recharges, the designation given to chargers that actually comply with, skip forward to the slide two, the Office of Low Emissions Vehicles, or OLAV. So there's an installation grant so that those chargers can comply with the smart requirements, and in a basic sense, those chargers can be controlled remotely and secured remotely, and that therefore will help support grid flexibility in a very summarized way of putting it. So a third party could turn your charger on and off, as Carbon Co-op's doing with the Power Shaper project, and that then can enable a shift in use. And then obviously if you stack up the shift in use across hundreds of EVs representing, you know, some of the highest loads in a property, that can be a significant amount of load shifting, which adds up to, you know, a huge amount of support for the grid and a massive modal shift as well in power. So yeah, if a third party can do that, then you'll support creation of flexibility, but you'll also support distributed energy from coming into the local grid, so a much more smart and flexible local grid as well, and a decarbonising of electricity in the mix. So, you know, we can take an advantage with that level of flexibility, you know, with a smart meter as well involved, every half an hour incremental shift. You can actually support on a windy day, if there's a big change in power use, you know, you could be supporting that too. So it's that kind of level of flexibility that this has a role to play. So EVs aren't just about, you know, going from A to B. They have so much more potential. But we have, you know, we've talked a lot about appliances that will meet our energy needs. All right, here's a a bit of a joke here from Ben, who created this part of the talk. So again, cars are not the only answer. It has to be said, we need a modal shift away from just using vehicles, and there are lots and lots of other solutions out there. One of the ones that I think is very popular in Carbon Co-op with the staff, but also beyond us hopefully, are the evolution of e-bikes. Not only does it have really low carbon emissions, but you can get places really fast, and they're very, very clean, and they're also pretty good for road space, and they look quite snazzy, some of them. You know, you might actually want to buy one of these. That, you know, it's not as glamorous as maybe some of the EVs out there, but they are still pretty amazing. And as a bike fanatic, I am biased, but yes, I'm not so keen on electric scooters on a personal level, but they are due to become legal in the coming years in the UK. And you might have noticed lots of people, or a few people, whizzing around on them. I find them a bit terrifying, but again, they take up very little road space, and they're an incredibly low carbon form of transport. And they obviously, it's a massive modal shift that they could support in terms of you know, how we are utilising our roads. It's already been proved building more roads doesn't decrease traffic intensity. So, you know, I think the argument's been won there. So quickly moving on to integration of home energy systems. How much time? 5 minutes. Goodness me, sprint to the finish line. So, you know, we've thought and talked a lot about how we need appliances that will meet our energy needs, our transport needs, but we need to put all of them together and see how we can control and coordinate them. And that really is the issue, because at the moment that's still the most difficult thing to do. So with the exception of EVs, you know, we do have smart enabled communication systems, but what we've looked at don't necessarily have the capability to work together well. So there's sort of this garden wall issue where some things want to talk to other things and other things won't talk to each other. So, you know, it is something that's very much still in progress, and there are lots and lots of factors involved in these. So, you know, why can't our requirements for systems talking to each other just be met, and how can we optimize our energy systems that we have already in home? So in terms of considering some of these factors around the appliances and how they function together as a system, this is a complex system here in that we've got external and internal issues, so changes in household energy use, the weather outside, preferences of users. You know, your home energy appliances can only take into account some of these factors, and they can do that at the moment still in quite a limited way. So that translates into a control requirement, which is really hard still for these appliances to meet as a system, you know, as a fully coordinated system. If they were all working together in a sort of perfect orchestra, and we had the perfect sort of back-end architecture, we could make these speak to each other, all of our systems work together perfectly. I mean, that is the home of the future, and it could be a very, you know, near possibility, but it's still something that will have constraints within itself as a system. So quickly skip through. So, you know, why we need, or what the need is. So the need for the system integration is obviously we do still need better monitoring and control and consumer experience. We need more optimal operation of our groups of appliances to help reduce costs, but also meet our needs. And appliance manufacturers aren't necessarily always really good at this, because they don't necessarily want things to be open source code or easy to connect with other things. Case in point, Apple being something that's not interoperable. So there is a reason for this. We want to trap consumers in product systems in product ecosystems if we're a designer of a specific product. We don't want our product to be superseded or connected with something else. We want it to just be our brand, for example, because that's our income stream. So so we could have, obviously, we can look at what's working in some contexts in the smart energy home of the now, if you like. So I can lay claim only to having the Hue Phillips app right now with my lights, because I think it's quite nice to have remote control of my lights, to be able to dim them. I just really like knowing that I'm conserving power and I'm using the least amount possible. And yeah, having that kind of I don't know, sort of subtle control over something's quite nice. Amazon Alexa is one that you all might be familiar with. Google Nest, Smart Things. So there's all these products are out there, and they, you know, some of them have a synthesis with existing products and services. But again, as I mentioned, that sort of garden wall effect. There is the vendor lock-in issue, and you know, there are concerns around data security, surveillance, you know, and these kind of practices which tend to capitalize on accessing and using data from users in a way that may or may not be permissions. So, you know, there are obviously concerns as well as benefits around having smart systems and these sort of families of products. So yes, cybersecurity is a big elephant in the room for this. In terms of options today, there are a lot of options out there. You know, we've got the cloud API and local access systems. We're using that for our PowerShaper service. There are smart home energy systems, as we've touched upon already, from the really huge corporations that you'll be familiar with. And there are obviously other sort of third-party management systems, or you can try your own DIY services. So, for example, the Home Assistant, which has its open software or open source code, so you can utilize that to make things speak to each other in your house that are smart enabled. So here's some examples of a family of smart products that work well together. So this is not a sponsored ad, it's just a worked example of the My Energy products, which are manufactured in North Wales. So a Zappi charger on the left, which is the EV charger. You've got your hub in the middle, which is what sort of speaks to everything and makes everything work together. And then you've got like a smart immersion controller on the right. And obviously the hub is the most important thing, because that's a way of measuring your energy use and sort of synchronizing everything nicely. So that system that you just saw was back is the kind that you can hopefully expect to see moving forward. But the only caveat is, again, we are stuck in this. If we use it, we're stuck in this My Energy world, which is nice. But again, it's functional, but it's not necessarily future-proof. And yeah, you're stuck with this one product company. So we'll whiz through to questions. Sorry, that was really rapid, but I'm really aware of time. Oh, nearly finished on time, but we'd like to launch a poll now. I forgot to launch the poll because of time. Sorry, Rich. Trying to speak as quickly as possible. So sorry about that if you guys struggled to keep up, because it was a bit of a whistle-stop tour. Should we take any questions because of time? How are we doing?
Yeah, we've got 2 questions. So Ian has asked, where can I buy a CAD and what does it do? What can I do with it?
That's a good question. Rich,
So
I'll let you be a little more technical of this.
Yeah, so a CAD, consumer access device. Basically, your smart meter will communicate. It sets up a thing called a HAN, a home area network. And Zigbee is the protocol on that. And it's like a kind of a Wi-Fi system. And a consumer access device will generally tap into that network that it sets up and will allow other devices to get access to the smart meter sensors, and it'll give you very, very high resolution data on your energy consumption. You can buy them off the internet. You can buy them. There are sort of ecosystems, as Polly's been saying, these kind of walled garden product ecosystems that will do smart home automations and so on. Very clever, endlessly clever things, and look very swish. But the first thing you need to do is to check that your smart meter will accommodate that, because some people have found that they buy these things and then they can't get them to communicate with their smart meter. And a lot of the smart meters are sort of locked down by the energy suppliers. So do check that first. If you don't want to be dealing with all that, then an alternative is to just install your own current monitors, and you can buy systems where you can put, without needing to cut any wires, without needing any kind of permission from anyone, you can put current sensors around wires in strategic places and monitor your energy use that way. And there's a whole open source ecosystem around that from Open Energy Monitor, the organizations. You can look them up. Otherwise, CADs are produced by companies called Chameleon and Geo are the main producers of CADs, but there's also a system called the Glow Home ecosystem, and you can just buy Glow Home CADs off the internet. So yeah, I hope that gives you enough to be getting on with. By the way, if anyone else wants to ask a question, do feel free to use the raise hand feature. And also perhaps, yeah, I'll just ask, there's another one here. Also, if I wanted to primarily charge the car with solar power, this is from Alex. If I charge my car from solar power, should I avoid a Type 2 charger? Normal AC charging uses 2.4 kilowatts and solar doesn't always exceed that. No, I wouldn't say that the choice of your plug should be affected by the capacity of your solar panel. The choice of your plug is really sort of set by the variety of cars you want to be able to accommodate with it. So I think the Type 2 plug is probably fine. You probably won't need fast charging at home. It really depends on your situation. It's unlikely you'll use fast charging, but a Type 2 I think is the widest, sort of the most common plug. So don't avoid it for the sake of your solar panels. If you want to make sure that you don't drain more energy than your solar panels are producing, then you can get systems in your charger that will clamp it and that will sort of sense how much you're generating and will charge accordingly.
Thank you, Rich. That's very comprehensive.
I hope so. Okay, if anyone else wants to put hands up, we can also hang around. I mean, obviously we're sort of up against the time that we specified, but we'll hang around for a bit afterwards. But we've got a few more things to run through, haven't we, at the end?
Yeah, we have actually.
And so on.
So we were going to just check in and see if anybody had changed their minds about the kind of home energy appliances or systems they might be thinking about investing in since the talk. I mean, you can type in the chat if you want or put your hand up. It'd be nice to know that, wouldn't it, Rich?
Yes.
We'd like to see if we've influenced you in a good way, hopefully.
Yeah, do feel free to chat.
Also, we'll be sending around a questionnaire for people, just a really short sort of feedback form, and we'll also be great, interesting. Thanks, Guy. So Simon says heat pumps, ground or air, and solar PV. Good to know. And are you finding the next steps? Thanks, Rich. And also looking into thermal batteries. Great. Yes. Inside of chemical ones. That's a good one.
Yes, I mean, if anyone out there is thinking of taking a hot water tank out of their house, stop. Don't do it. If we did go through a while where people were taking hot water tanks out of houses, but the latest kind of, the most cutting edge house designs, putting them back in, smart immersion tanks, brilliant things.
Is it because hot water storage is still the most efficient form of
absolutely
energy storage?
Decent control on that. Yeah, I'm a big fan of hot water.
Yeah, absolutely. Insulation reduction first.
Simple
absolutely
solutions.
Yeah.
Okay, we've got some next steps for you. I think most people are sticking around. So we've got some other upcoming events here. Hopefully you can see that. Beginner's Guide to Retrofit, 8th of July. It's another webinar. So if you are interested in what you can do to make your house more thermally efficient, then do sign up for that one. 8th of July, 6 p.m. to 8 p.m. And if you're interested in heat pumps, which I know a lot of you are, We've got a webinar about retrofitting domestic heat pumps there on the 24th of June. That's not very long at all. I mean, as in not very long away. That's the day after tomorrow or something, or it's this week anyway. 5 p.m. 6:30 p.m. So you can find them on our website, carbonco.com/events/list, and sign up from there. It'd be great to see you at those events. Finally, if you can get notifications about other trainings by signing up for our newsletter, following us on Twitter or Instagram. Polly has mentioned, do you want to have a plug for the Power Shaper project, Polly?
Yes, please. We're working on a fantastic project which we kind of touched on in the presentation, where your EV or your immersion with hot water tank, your electrical immersion, can be used to help sort of shift energy use through a smart controller. And if you join Power Shaper, we'll also £150 of vouchers, which is quite nice, but you're supporting our research and development into how we can support local flexibility and smart grids development. And it's a really simple project to join. It's like a five-step attendance. So you just go through an enrolment form, and then hopefully we can get you on board, and the installation is free. So the whole process is supporting the testing part of the service as it develops. So all you need really is an EV, or you don't have to have an EV, but also an immersion heater. If you've got one of those and it's electrical, then we'd love to hear from you. And you can just email, info@carbon.coop or powershaper@carbon.coop, or Polly, it's fine, whichever one you prefer. But the email's up there for you. So we'd love it if you could help us with our project. And it's an innovation project, so you'll be supporting us to develop that research as well. And Rich, do you want to add anything?
Well, just carry on. You can see the rest of this here. Attend an Eco Home Lab session, second Thursday of every month. We run those, even during lockdown. They're all online now, though. Join Carbon Cult. We are a membership organisation. We have, as I say, 250 plus members. It'd be great to count you amongst them. Give us feedback. Right, we've got a feedback form as well. Polly, have you got that to hand? We're going to put that in the chat. So if you'd like to give us feedback, what you thought of this, I know it's a lot of content and we've kind of rushed through it, but I hope that's not been too unpleasant for you all. So yeah, we'd love to hear what you think about it. If for more detail, email us on info@carbon.coop. And also, this was a free event and we're very pleased to be doing it. And as I say, this is the fourth time we've done it, so we're kind of honing it. But if you did think it was worth a few bob, if you'd like to pay, then do feel free to drop us a few quid in the hat. This is us passing around the hat at the end of the show, as it were. So don't be obliged, but I'll put a link in for that too there into the chat. So okay,
we'll send all of this as well, won't we, Rich, in an email with the slides, and you'll be able to catch the recording as well on our YouTube account. I think now we've moved everything. Right, we've moved away from Vimeo, but yeah. Please forgive us, and please follow us on YouTube if you utilise YouTube. That'd be lovely. Always nice to have that. Anyway, thank you, everybody.
Yeah. Otherwise, if there's, Paul says we've got the wrong date for the heat pump talk, have we? Oh gosh, that would be embarrassing. Okay, I'll confirm that.
Oh yeah, you are correct. It is. There's a heat pump talk taking place on the 30th with Florence Collier. That's fine. Thank you for mentioning that.
So, my apologies there. I don't know where I got that information from.
That's okay.
Oh well.
It's a Monday.
Okay.
That's my excuse. Well, thank you so much, everyone, for joining us.
Yeah, and please do give us feedback and let us know what you thought and anything you found useful, anything you didn't find useful. We're here. We'll be sort of sitting here for another 5 minutes or so in case anyone wants to ask any questions. Hands up or in the chat or Q&A. But otherwise, thank you very much for attending.
Yeah, thank you, everybody. Really nice to have you here.